Hello. Good evening, Charan.
Good evening, sir.
Right. Okay. But, okay, let's start now. चलिए अब आप चलिए.
मैं
Okay.
बैठ जाऊँ 5 मिनट अभी ना कोई
Okay.
के 5 मिनट है
Right. Okay, let's start now. So, in the last class, we discussed up to what? Up to the work energy theorem, isn't it? And in the work energy theorem, what we do? We relate the work done by the forces with the kinetic energy of the particle. Okay. This is the last example I gave. Did you try this question? Please tell me. Tried this question? So this spring gun was compressed by 50 centimeter and released, right? So what will happen when it will leave the spring? The block must have gained some kinetic energy in the process, isn't it? So what will be the kinetic energy of the block when it leaves the spring? So let's first calculate it. So we can apply half mv square minus initial kinetic energy 0, and that should be equal to work done by all the forces. If you see, the spring is already compressed by 50 centimeter, and normal and mg are what? Perpendicular to the displacement. So normal and mg work done will not come, only work done will come by the spring force, and spring is compressed initially, and now it is going to gain the natural position. Okay, so that will be work done by spring. How much it will be? Half k x square. That's it. Half and half get cancelled out. So what is the velocity of the block? The velocity of block is under root k by m into x square. Now let's put the value, isn't it? So what we are getting? Under root of k by m into x we are getting. Now what is the k given in the question? K is given 100, mass is given 4 kg, and what is the x? X is the compression, which is 0.5. So 25 square root, if I take it to 5 into 0.5, that means 2.5 meter per second is the velocity of the block. Once it leaves the spring, then it will just follow the projectile motion, isn't it? So in the projectile motion, we just need to solve the projectile motion now, isn't it? So this is a projectile motion where particle is thrown horizontally with what velocity? 2.5 meter per second. So it will reach the ground somewhere here, isn't it? And they are asking the question distance from the table. That means this horizontal distance they are asking, and this height is given as what? 10 meters. So first of all, we will calculate how much is the time taken to reach the ground. Time will come under root of 2h by z. So 2 into h by z. So root 2 second it will take to reach the ground. So in that process, what will be horizontal displacement? So horizontal displacement will be horizontal velocity into the time taken, right? So 2.5 and root 2 is what? 1.414. Right? We can simplify it. That much meter will be our answer. So here what they did, they related. अब जाइए बाबू अब आप.
कल
Yes.
1 मिनट हो गया.
हाँ हो गया. Okay. So here what happened? That work energy theorem related with what? Related with the projectile motion. So please tell me, understand this one? This was the last example given in the class. Okay. So now we have learned the one form of energy which is called the kinetic energy. Is that clear? And kinetic energy, how it is related with the work done? So using the work energy theorem, we can relate kinetic energy of the body with the work done by the all the forces. And what is the work energy theorem? As per the work energy theorem, change in kinetic energy is going to be what? It is equal to work done by all the forces. So please keep in mind, whenever you are applying the work energy theorem, you have to write work done by all the forces acting on the body. But sometimes it may be possible that let's say there are 3 4 forces acting on the body, but only two of them is doing the work. So write the work done by those two forces. The force which is not doing the work, no need to write it, or you can just simply say that that work done is equal to 0. Is that clear? Please tell me, clear up to this?
Yes, sir.
Right. Now let's discuss the another form of energy that is called the potential energy. Okay, kinetic energy we have discussed. So there are two form of energy, or we can say the mechanical energy has the two different form the mechanical energy of a particle can be. What are those two different form? One is the kinetic energy, other one is the potential energy. Okay, so let's learn about the potential energy. Now, whenever we write the potential energy is only defined for what? For the conservative forces. Please keep in mind first condition about the potential energy. Okay, like the gravity is a conservative force, spring force is a conservative force, electrostatic is a conservative force. So that's why we can only define the potential energy of these type of forces. If a force is non-conservative, then we cannot define the potential energy of that force. First thing is about that one. Now the question is, which force can be called as a conservative force, right? So a force is called conservative if the work done by the force does not depend on the path of the particle. Means how the particle goes from initial to final point. If the work done by the force does not depend on that, if the work done by a force only depend on the force and the displacement of the particle. Okay, how the displacement happened, right? What path the particle has taken to cover that displacement. If it is not affecting the work done, then we will call that force is a conservative force. The first thing what we learn about the potential energy, the first thing is what? It is only defined for what kind of forces? Only defined for conservative force. Okay. Now the question arises, what is a conservative force? Conservative force means what? A force is called conservative. Okay. A force is called conservative, right? If work done by the force, okay, work done by the force is is independent of the path. Independent of the path. Okay. So how the particle has gone from one point to another point, if the work done by the force is not depending on the path, then we will call it that force is what? Conservative. So example of conservative force are what? There are few examples of conservative force. The most common conservative forces we have is the gravity. Gravity is what kind of what kind of force? It's a conservative force. Okay, the gravity is a conservative force. Next, spring force. Next, electrostatic force. Okay, na. So we can only define the and any constant force. Any constant force. If a force is constant, then it will be obviously going to be a conservative one. A constant force can never be non-conservative. Okay. So any external force, if it is a constant one, any external force, if it is a constant force, then we can call that force to be what? A conservative one. So any constant force is what? A conservative force. Okay. So now, how do we write the potential energy? Now, the first question is what? What is the potential energy? So please keep in mind, we always define what? The change in potential energy. Okay. What we define? We always define the change in potential energy. Like, let's say a pen is there on my palm, right? Now, if I take this pen above the palm, then what will happen? Am I doing some work? Please tell me, this pen is not going by its own to the some height, na? It means I must be doing some work. So the work I am doing is against what? Against a conservative force. Which conservative force? The work I am doing is against the conservative gravity force, isn't it? The work we are doing is against a conservative force called gravity, right? So that's why here what will happen? The work done against that conservative force will be what? It will be stored in the form of potential energy. So please keep in mind what is the potential energy. So change in potential energy is equal to equal to work work done against the conservative force. Okay, how much work we are doing against the conservative force? Okay, na, what is the work we are doing against a conservative force? That will be stored in the form of potential energy. Okay, so potential energy of a body can be increased, potential energy of a body can decrease as well. Okay, so when it will increase and decrease, it depends on what is the work done by conservative force. Okay, so change in potential energy is equal to work done against the conservative force. Work done against the conservative force. That means in the symbolic form, you can write it delta U. Delta U is what? Change in potential energy. Against means negative sign. What we can write it? Negative of work done by CF means what? The conservative force. Okay. So if I can calculate what is the work done by conservative force, let's say work done by conservative force is positive. So minus of that positive work done, that means what is the delta U will come then? Then delta U will come negative. So if work done by conservative force is positive, potential energy will decrease. If work done by conservative force is negative, potential energy will increase. Think about this pen. If I'm taking this pen up, okay, if I'm taking this pen up, what does it mean? Is the gravity is doing negative work now? So potential energy of the pen will what? It will increase. Understood? Every time writing the difference in potential energy or change in potential energy is a little bit difficult. So that's why what we do, whenever we write the potential energy, what we do, we take a point as a reference. Okay, we take a point as what? We take a point as, or we take a line as what? The reference. How? Let's see. First of all, do you understand what is the definition of change in potential energy? Now we will write the potential energy of these three common forces: gravity potential energy, spring potential energy, and electrostatic potential energy. Electrostatic potential energy we have discussed in many details, isn't it? Electrostatic potential energy, electrostatic potential, remember? Many times we have applied the work energy theorem, energy conservation. So those forces and its potential energy we have discussed in detail, right? Now let's discuss about what is the gravitational potential energy. So three type of potential energy we are going to discuss now. The first one is what? The gravitational potential energy. When the gravitational potential energy is going to increase and when it is going to decrease, let's try to find out. Okay, let's say an object is kept on the ground. Okay, let's say an object is kept on the ground. Mass of the object is something m. This is the initial position of the object. Now this object is taken something like this, somewhere here the object has reached. Let's call this is the final position of the object. And the height difference between them is what? Something h. So if I ask you, what is the change in potential energy? You should always first answer about change in potential energy. Then we will put a reference point, and after that, change in potential energy will be converted into just the potential energy. Okay. So if I write it delta U, what you will write? Negative of work done by conservative force. Can you tell me what is the work done by conservative force here? So work done by conservative force means what? Work done by gravity only, because here I'm talking about the gravitational force, isn't it? How much is the work done by gravity? Is the work done by gravity is minus mgh in this case, because initial point and final point, what is the difference in height? H. And work done by gravity only depends on mg and height difference. It does not depend on the path. Reason is what? It's a conservative force. Okay. So delta U, how much we are getting? Minus from the definition, and work done by conservative force, which is another minus mgh. So that means what? If I calculate the change in potential energy of this object in the process, can I write it? U final minus U initial, and is it coming mgh? What does it mean? That means what? That this object potential energy got increased by mgh. When I take this object h height above, what happened? This object potential energy got increased by how much amount? mgh amount. If this object is taken h height below, h depth below, then potential energy decreased by how much? Decreased by mgh. Now, here, if I say this is, I'm going to take it as a reference potential energy. Let's take reference potential energy as 0. Generally, when the object is on the ground, what we do? We take its potential energy to be 0. If I take U initial as 0, then what will happen? U final will become mgh. So this is what you remember as the formula, that when object is taken height h above the surface of earth, we say the potential energy of object got increased by mgh. But actually when you are writing that, you have taken your reference as what? You have taken your reference as ground, and the ground potential energy as what? You have taken it as a 0. Understood? Please tell me. But it's not necessary. We can take any point as what? The reference. Any initial point we can take it as a reference, And from that reference, if particle goes h height above, potential energy increases by mgh. From that reference, if the particle goes h depth below, potential energy decrease by mgh. Understood? So if I say reference is 0, so h height above, what will be the potential energy? Plus mgh. And if reference is 0, h depth below, what will be the value? Minus mgh will be there. Understand the gravitational potential energy?
Yes,
This is
sir.
the gravitational, okay? This is the gravitational potential energy between Earth and particle. Between what? Earth and particle. Now, between the two planets or two very far away object or very heavy object, what will be the potential energy? If m1 is the mass of the first particle, m2 is the mass of second particle, and if these two particles are distance away from each other, what will be gravitational potential energy? So minus C m1 m2 by R will be there. But here in the work energy power, you will see most of your question involved gravitational potential energy of Earth and any small object. Matlab, the object whose potential energy we are calculating is very small compared to Earth. If two comparable mass is there, then we should write it minus C m1 m2 by R. Like Moon and Earth, we want to write it. So now you cannot write it mgh, है ना? You should write this G m1 m2 by R minus Z m1 m2 by R. So that is the gravitational potential energy. Next, second type of potential energy we are going to discuss is called spring potential energy. Okay, second potential energy we are going to discuss is the spring potential energy. So what is spring potential energy? Let's see. Let's say that an object is there, it is attached with a spring, and now what happened that this spring constant is k, mass of the block is m, and this is called the natural position. Understood? The natural position, or it is also called the natural length of the spring. Natural position or natural length means what? The position when the spring doesn't have any elongation or compression. Now what I am going to do it, I am going to extend this spring by how much? Something x. So what, this is my initial position, and after elongating by x, that becomes our final position. Understood? Initially, the spring is in this situation. Let's call it initial position as x. Sorry, initial position. And after elongation, let's call what we got it is the final position. Again, what I want to do, I want to write it change in potential energy. Okay, what is the change in spring potential energy from this initial to final? So I will write it minus from the definition. Next what I will write it? Work done by, right? Change in potential energy is what? Negative of work done by conservative force, which is the spring force here. So what is the work done by spring force? If you elongate the spring or if you compress the spring, so that is minus half kx square. That is what we have been using, Hannah, from long time, isn't it? Work done by spring. Please keep in mind what I am writing here. Work done by spring. Okay. So what I got it here, we are getting half k x square means u final minus u initial is what? Half kx square. That means when the spring is elongated from its natural position, okay, or if spring is compressed from the natural position, what happened? Then now this spring is stored what? Some extra energy. Understood? Compared to initial condition, okay, compared to initial situation, in the elongated situation, spring stores extra energy, or that energy will be called spring potential energy. Understood? The change in potential energy is this. Now if I say U initial is 0, means what? What is the reference I am taking? I am taking reference as the, what is the reference for potential energy? I am taking reference potential energy 0 at the natural position. Means what? When the spring is in its natural length condition, or when the spring is in the natural position, that time what I am considering the spring potential energy as 0. If I take U initial as 0, then what happened? Then U will become, final will become half kx square. So that's why if spring is elongated by x or it is compressed by x, both case. Okay, if spring is elongated by x or spring is compressed by x from the natural position, now the spring is storing extra energy. How much is that extra energy? Half kx squared. Understood? So, in the elongated or compressed position of the spring has extra energy which is in the form of potential energy. Next, the third one, electrostatic one, that we have discussed in many detail, isn't it? What is the electrostatic potential energy between the two charged particle? Because again, electrostatic force is what? Conservative in nature, isn't it? So what is the electrostatic potential energy? So if two charged particle Q1 is there, Q2 is there, and separation between them is R. So what will be the electrostatic potential energy between them? K Q1 Q2 by R. Again, what is the reference here? I will say, sorry, here no reference. Yes, there is a reference here also. What is the reference here? Reference here is what? That when the charged particle are infinite distance apart from each other, then their potential energy is 0 taken. Same thing here. When the two particles are infinite distance away from each other, their gravitational potential energy is taken as 0. Understood? So this is the potential energy thing, isn't it? Potential energy, whenever we calculate, right, we should keep in mind that we are only calculating the potential energy for what kind of forces? The conservative forces. And what kind of force is called conservative? If the work done by a force is independent of the path, that force will be called as conservative in nature. Understood? Now, conservative force and potential energy, there is a relation also. There is a relation between what? The force and the potential energy. Okay, let's discuss that one. So, sometime what will happen? They will give you the relation of potential energy, then they will ask you what is the force, or sometimes the force will be given in the question. They will ask you what is the potential. Okay, so let's try to learn relation between conservative relation conservative force and potential energy. Okay, let's try to learn the relation between the conservative force and the potential energy. What we know about the change in potential energy? Do we know change in potential energy is negative of work done by conservative force? Please tell me, can we write it like this? Okay, if I want to write it in the differential form of delta U equal to minus of work done by conservative force, that is for a big amount of work done and big change in potential energy. In differential form, can I write it du equal to minus of, can I write it dw conservative force? Please tell me. Change in potential energy, a small change in potential energy will be equal to what? The negative of a small amount of work done by conservative force. Now you see here du equal to minus. What is the definition of work says? Does it say the definition work done, a small amount of work done only we are writing now. Right? The small amount of work done we are writing. So can I write it? F into dx can be write it. So you can also du equal to minus of f dot dx. But please keep in mind the f I have written now. What is this f? This f is the conservative of any kind of force. It's what kind of force? This f is what kind of force? It's a conservative force. So can I write one more thing? F equal to minus du by dx. Listen. So if force is given, you can find out change in potential energy integrating it, right? Or sometime what will happen, potential energy is given to us. Then by differentiating the potential energy, what we can get the value of the current. Okay? Energy is given as a function of x, we'll do it du by dx. If it is a function of y, du by dy. Sometimes it may be possible that potential energy is a function of x, y, z. All three types of variables are involved. So in that situation, what we should do? We should find the force by what? By partially differentiating it. Means if I differentiate potential energy with respect to x, that gives us the force in x direction. Then again, we'll differentiate it with respect to y. It gives us force in y direction to us. Understood? Now, one last thing we will discuss now, and then we'll go for the question. That is called conservation of mechanical energy. Okay? Up to this part is clear?
Yes.
Let's discuss the one more thing. It's called conservation of mechanical energy, or it is also called as the conservation of total energy or conservation of total mechanical energy. Okay. Now, when we can apply the conservation of mechanical energy? See, conservation of energy, sometimes it is also called conservation of energy or conservation of mechanical energy. Actually, conservation of mechanical energy or conservation of energy is a special case of work energy theorem. Okay, conservation of mechanical energy or just conservation of energy, it is just a special case of what? The work energy theorem. Means what? Work energy theorem is applicable everywhere. In all the conditions, we can apply the work energy theorem. But if some special condition of work energy theorem is met, then what we can do? We can apply the conservation of mechanical energy. Okay, conservation of mechanical energy is just an special case of what? The work energy theorem. Understood? So what is that special condition needed to apply the conservation of mechanical energy? Let's try to learn that one. Okay. Okay. So conservation of mechanical energy is what? It is a special case of what? The work energy theorem. Okay. What is the special about the conservation of mechanical energy? Now let's try to understand. Okay. Now tell me, what is the work energy theorem? What is the work energy theorem? Tell me. As per the work energy theorem, can I write it? K final minus K initial. Right? What is the work energy theorem? Work energy theorem says that change in kinetic energy, that means K final minus K initial will be equal to work done by all the forces, right? Okay, let me write it something like this. Can I write it K final minus K initial equal to, all the forces are there in the position, right? let's say there are 4 forces acting on the body. Out of the 4, let's say 2 of them are conservative and another 2 are non-conservative. Okay, or maybe possible 1 is a conservative force, 3 of them non-conservative. Or it may be possible 3 are non-conservative, 1 is conservative. So it depends that what are the forces acting. So let's say all these I am going to divide into 2 parts: conservative force and non-conservative force. Clear? Let's say there are n number of forces are acting, 5, 4, 3, any number of forces are acting, but all these forces can be divided into 2 parts: conservative and non-conservative. So the right hand side of the work energy theorem, which was earlier saying work done by all the forces, now that same expression I have just converted into conservative and non-conservative. Now the speciality arrive. What is that? Now, in this case, if work done by non-conservative force is 0, okay, if, see that, work energy theorem, any condition is there, like I should only apply for this case, or this case only I should apply for gravity force, or I should only apply for friction, I cannot apply for resistance force. No, work energy theorem I can apply everywhere. So if I'm applying the work energy theorem and when I saw the question and I found it that there is no work done by any non-conservative forces, please listen it carefully. If in a question non-conservative forces are not doing the work, now see, then what it will become? Then is my equation became k final minus k initial equal to only work done by conservative force. And you know one more thing, k final minus k initial, work done by conservative force can be written as minus of change in potential energy. Do you agree? Just little bit earlier we have defined the conservative force. Potential energy we have defined. We have written change in potential energy equal to negative of work done by conservative force. So the work done by conservative force can be also written as minus of delta U. So if you write it little bit further, K final minus K initial equal to minus what is the delta U? Delta U means change in potential energy. Let's just write it change in potential energy. Can I write it change in potential energy as U final minus U initial? Send it one side. K final, look at that. If I'm sending U final other side, am I getting K final plus U final equal to? Am I getting K initial plus U initial? Check it. What did I just written? K final plus U final. An object has only 2 form of energy. An object has only the 2 form of energy, kinetic and potential. The left hand side we have sum of kinetic energy and potential energy equal to right hand side again sum of kinetic energy and potential energy. So does that mean if there is no non-conservative force doing the work, then what will happen? Total energy, or can I say that is remaining conserved, means K plus U will be conserved, you can say that, or you can also say that total mechanical energy is conserved. But to apply the mechanical energy conservation, what is the condition needed? The first and only important condition for applying the energy conservation is what? That there should not be any kind of work done by non-conservative force. If any non-conservative force is doing the work, don't apply the work energy theorem. Sorry, don't apply the energy conservation. Can I apply work energy theorem? Yes. Work energy theorem is always applied irrespective of conservative or non-conservative forces doing the work. Understand? But energy conservation, it will be only applied if there is non-conservative forces work done zero. So please tell me, understood up to this what we have discussed? Now let's discuss some example now. And you see, did we apply this energy conservation many times in the electrostatic chapter? A charged particle is sent towards the ring charged, है ना? What will be the velocity of the particle after one point to another point, right? All these cases you have seen, the only force involved in the question was electrostatic, and that is conservative in nature. So that's why we were applying the energy conservation very frequently in those situations. Understood? Let's discuss some examples now. Okay, let's take the first example where I'm going to give you and ask you what is the force acting on the particle. Okay, clear? Understand how do we write the potential energy we have learned, right? Energy, electrostatic, gravitation, or potential energy we have written. Chaliye, let's say in the question what is given, potential energy of a particle is given 3x squared y plus 4yz plus 3x cube z squared. X cube z cube given to us. You see, potential energy of this particle is a function of what? X, y, and z. So that means on this particle, there is going to be force in x direction, y direction, as well as in the z direction. So now they are asking in the question, and that force is also variable in nature. Okay, to find, and which force? Conservative force, obviously, because I have given you the potential energy. It means if I am giving you the potential energy, that can be only given for what kind of force? Conservative force. Okay, find force acting on the particle on the find the force acting on the particle, and that force is variable in nature, so I must give you the coordinate also, isn't it? I must give you the coordinate also. To find force acting on the particle located at 1 comma 2 comma 1. Okay, 1 comma 2 comma 1, simple values are given to us. Particle located at 1 comma 2 comma 1. Chili, please try it and tell me. Here you see potential energy is given as a function of x, y, z all. So you should do the partial derivative to find out the uh, force acting on that. Okay. So please tell me how much is that coming. So please tell me how much is that coming? What is the force coming?
Yes, the 1 minute. Sir, minus
How much is
21i, minus 21x, minus 7y, minus 17j.
okay? So how do we calculate this one? So if I'm going to
Okay.
calculate the force, we should do the partially derivative, है ना? If I'm writing force in x direction, I will write it minus du by dx. Means I have to differentiate with respect to x. So whenever we are differentiating with respect to x, x will be the variable and remaining everything else will be what? The constant. Understood? That is the meaning of the partial derivative. So how much is that coming? Minus. First term, 3 constant, y constant, x square differentiation 2x. Second term, y, z, both are constant, है ना? Because we are differentiating with respect to x. 4y, z, all three constant, plus 3z cube constant, x cube differentiation 3x square. So we have how much? Minus 6xy plus 9x square z cube. That is the force in x. Now let's find out force in y. So we will write it minus du by dy. That means now my variable will be y and everything else will be what? The constant. So dy 3x plus 3x cube z cube. Differentiate it minus first term 3x square outside, y differentiation is 1 plus 4z outside, y differentiation 1, and third term differentiation 0 because all are constant term involved here. So we got it minus of 3x square plus 4z. Now we'll calculate fz. Fz means now we have to do the differentiation with respect to z. Partially we have to differentiate with respect to what? Z. So what we will write? Minus d by dz. First term is 3x square y. Second term is 4yz. Third term is 3x cube z cube. Differentiate it minus outside. First term z is the variable. So 3x square y all constant. So its differentiation will be 0. So whenever you do the partial derivative, you do it partially with x, y, z. And when you are doing the partial derivative with x, that means x is your variable and anything else in the expression you have, that you will treat it as a constant one. Okay. The first term differentiation 0. Second term 4y outside, z differentiation 0. Third term 3x cube outside, z cube differentiation 3z square. So we have minus 4y plus 9x cube z square. So this is the force we have. Okay. Fx we will write it with I cap, Fy with j cap, Fz with k cap. So what is the force we have? Now I can directly put the value, right? Where I want to calculate Fx, I want to calculate Fx at 1 comma 2 comma 1. So minus x is 1, y is 2. So 6 into 1 into 2. So 12 will come plus 1 1 to 9. So we got it how much? Minus 21 we got it. Fy again where I have to calculate 1 comma 2 comma 1. So minus x equal to 1 to 3, 4 into 1 to 7 it will come, है ना? 3 plus 4. And same thing you can do it for the z. Into 2, 8 plus 9, है ना? 17 will come. So what is the force acting on the particle at that point? So at that point, the force acting on the particle is, what is the x? Minus 21. So minus 21 I cap you can say that. Y minus 7 j cap you can say. and minus 17 k cap we can say. So this is the force acting on the particle at that particular point. If they don't mention the point, then whatever the x, y, z kind of expression we got it, same in the expression format we will be writing our answer. Understood? Let's discuss another example. In this example, what is given to us? A chain is given on the table. Okay, there is a smooth chain is given, smooth table is given to us. Okay, right now I am taking this smooth one. Next class I will take an example where I will take the table as the rough one. Okay, here the table is what? The smooth. If you push it slightly, what will happen? Is the chain will slide, and finally what will happen? It will fall down. No? The question they are asking, find the velocity of the chain. Find velocity of chain when it completely slips off the table. Completely slips off the table. Understood? So here you see that the only force involved is what? The gravity. And it's a uniform chain. Okay, na? Uniform chain. So, and mass of the chain is what? M. Length of the chain is what? L. So now tell me, only the gravity force is involved, isn't it? Which is a conservative in nature. So I am going to take this as my reference for gravitational potential energy as 0. So initially, can you tell me what is the kinetic energy? Can I apply the energy conservation here? K initial plus U initial equal to K final plus U final. Initially, chain is stationary, 0 kinetic energy. Initially, the complete chain is on the table, so 0 potential energy, because the table is acting like the reference of gravitational potential energy. Finally, when the chain will slips, it will have some kinetic energy, half mv squared. And what is the potential energy of the chain? So it is below the reference point, na? So minus, है ना? Above the reference point, potential energy positive. If it goes below the reference point, potential energy negative. Exactly on the reference point, 0. Okay, so it is going below, so that's why minus. How much minus? Mg into L by 2. How this L by 2 comes? Because when the chain will slip, this is where the center of mass of the chain will be. And it's a uniform chain. The center of mass will be at the midpoint. So right now, just keep in mind, the next topic when we will start is going to be our center of mass. After completion of our, then we will learn to calculate the center of mass of different body. Okay, so that's why this is what we have written. Just we need to simplify it. What are we getting? Half mv square equal to mg L by 2 we are getting. M and 2 get cancelled out. What is the velocity of the chain then? We have root GL as our answer. Next class we will also learn about, by considering, if there is a friction on the table. If there is a friction on the table, can I still apply the energy conservation? No. But can I still apply the work energy theorem? Yes. Okay, because when the friction will come, friction is a non-conservative force, then we won't be able to apply the energy conservation, but still we can apply the work energy theorem. Okay, so let's do it the next class, and we will continue with this one. Okay, in the electrostatics part, electromagnetism part, we were in the RC circuit, which we will continue tomorrow in the class. Okay, right,
Okay,
everyone?
sir. Yes, sir. Thank you,
Great.
sir.
Thank you so much, everyone, and let's meet it tomorrow.